Linux Application Programming Series, Session 15, Shared Memory Programming. That means we are going to talk about the memory area to be shared among different processes. How do we create, how to manage, how do we handle? This session is all about that. Introduction to shared memory, creating and configuring shared memory edge segments, using and protecting shared memory segments, locking and unlocking shared segments, and using ipcs utility and ipcrm utilities for shared memory. Same utility, just different options. Introduction. Shared memory allows two or more processes to share a chunk of memory so that each can communicate with all others. The address space for parent and child processes, though they are independent, but this shared memory gives you some area which can be shared between the processes. On GNU Linux, all processes have a unique virtual address spaces, but the shared memory API permits a process to attach to a common address segment. With all this power comes some complexity. For example, when processes share memory segment, they must also provide a means to coordinate access to them. This is commonly provided via a semaphore. That's what I was talking about, the locking mechanism or token concept, which can be contained within the shared memory segment itself. The shared memory. Let's create a shared memory segment, get an identifier for an existing one, configure a segment, attach it and detach it, and some examples of processes using that. So in other words, this is a complete walkthrough, as we have been discussing for the other topics also, a quick hands-on example. We need function prototypes and symbols to be available to the application, and for that two header files are there. One is ipc, second is shm.h. These are for header files. Creating a shared memory segment. The program available in your source code files under directory session 15 src shmcreate.c. So this is the program. If you look at here also, we are creating common.h, a header file. We are declaring a normal integer and we are creating the shared memory shmid, shared memory get, and process. The command, this function call, is similar to semaphore shared message queue. It's similar here also. So we use shmget API function. We specify a unique shared memory ID, that is my shmid, which definitely might be declared into common.h, the size of the segment, and the set of flags. The flags argument include both access permissions and a command to create the segment, that is ipc create. Getting information on shared memory segment. We can get information with shmctl API function. Let's first get the shared memory identifier for the segment using shmget API function. Once we have this, we can call shmctl to grab the current status. So retrieving information about a shared memory segment. This is the program where we include some more header files. Error.h, shm common file, and we are using shmget. So in this program, to shmctl we pass the identifier. This is our call to shmctl in line number 18. We pass the identifier shmid, which is called here, which is nothing but integer after setting it. So we are passing this and then we are using ipcstat. So we pass the identifier for the shared memory segment, the command to grab stats, that is ipcstat, and finally a buffer in which the data will be written. This buffer is a structure of type shmid underscore data structure underscore ds. On successful return of shmctl identified by a 0 return, we emit our data of interest. Here we emit the size of the shared memory, that is shmds and dot shm segment size sz, and we also emit this shm and attch, that is number of attach that have been performed on the segment, that is an attach. Attaching to a shared memory segment. Attaching maps the shared memory into our process's memory space. To attach to the segment, we use shmat function, API function. This returns a pointer to the segment in the process's address space. This address can then be used by the process like any other memory reference. We detach from the memory segment using shmdt API function, that is detach. So AT for attach, DT for detach. We'll use simple application to attach and detach from the shared memory segment. So this is the example for attaching and detaching, attaching to and detaching from shared memory segment. In the source code directory, the program is shmattach.c. This is the screen grab. We first get the shared memory identifier using shmget, line number 11, you can see here. Then we attach the segment uses shmat, which we are calling here in line number 14. What we are passing here is shmid and constant pointer, null pointer. We specify our identifier, an address and option word. After checking this, if this was successful, we detach from the segment using shmdt, line number 23, shmdt. Writing to the shared memory segment, shmwrite.c is the program for you. try this. So process, now you know the calls. We are declaring it shmget, shared attach, and then we are copying the data. String copy, some memory area. This is a test string copied to the shared memory, because shared memory is identified by mem after attaching it. Let's see an example that uses the string copy standard library function to write to the shared memory segment. Since the segment is just a block of memory, we cast it from a void pointer to a character pointer in order to write to it. That's why we use, in line number 19, we use character pointer. Reading from the shared memory segment. After copying this, we want to read the data from it. So SHM read is the program available on your system. So we are copying it here. So SHM ID, attach it, copy something printf, right, and detach it. So in this example, we are reading a block of memory by printing normal printf call, by passing the character pointer casting to the memory. The first process attaches the memory, writes the string, and then detaches and exit. The next process attaches and read from the memory. Removing the shared memory segment. To permanently remove a shared memory segment, we use the shmctl API function. You see the symmetry now. For past 2 days, whatever topic we are talking about, they have some kind of symmetry in the naming convention also, in the API calls also, parameters also. To permanently remove a shared memory segment, we use shmctl API function. We use the special command with shmctl called ipcrm to remove the segment. Once the shared memory segment identifier is found, we call shmctl with ipcrm. Same argument, only the function name is different. Concept remains the same. So this is in line number 14, we are removing it. shmctl, shmid, ipcrm. So these are the APIs which were used in the walkthrough. shmget to create a new shared memory segment and to get the identifier for an existing shared memory segment. shmctl to get information on a shared memory segment, set certain information on a shared memory segment, and remove a shared memory segment. SHM attach, that is AT, attach a shared memory segment, and shmdt to detach a shared memory segment. So let's just understand these API calls one by one. shmget API function. The shmget API function is a multi-role function. It can be used to create a new shared memory segment, and it can be used to get the ID of an existing shared memory segment. The result of shmget is an identifier that is to be used in all other shared memory functions. So this is what we use. So these are the arguments we need to understand. The way we understood rest of them, now it is self-explanatory. I am sure you understood it quite easily. The key specifies system-wide identifier. It must be non-zero value or a special symbol, IPC private. Same. The size argument identifies the size of the shared memory segment to create. When we are interested in existing shared memory segment, we leave this argument as 0. As a minimum, the size must be the page size of your operating system. generally 4 KB for example. So the shmget function, SHM flag argument in this function permits the specifications of two separate parameters, a command and an optional set of access permissions, which we learned. Now you see it is a copy paste from the previous topic. Create a new shared memory segment with SHM flag as ipcreate. This returns the identifier for a new or existing segment. If we want to create a segment and fail if the segment already exists, then we can use ipcreate with ipcexcl. You remember that existing symbol. That is second form. And third is simply request an existing shared memory segment. Now it is repeat is happening, and the same set of values we have here also. Symbol SIR user, that is read user permission, write permission, that is for user read and write, group read and write, and others read and write. So name of the permission. Find the symmetry, then it will be easier to read. Users, group, and others. Now user, grp, oth, right? So IR, that is read, write, W, RW, RW, RW. I is common. So S underscore I, then read user, IS underscore I, W user, S underscore I, R group, S underscore I, W group, then S underscore I, read others, S underscore I, write others. To memorize this, to learn this. When creating a new shared memory segment, each of the read-write access permission can be used except for the execute permissions. You notice that we are talking about read and write, not execute. Examples of shmget function that was there in the quick walkthrough also. This is another example. A new private shared memory segment of 4 KB with all permissions to all, that is system, group, and user. The call will be something like this: IPC private 4096 IPC create and the permissions. If the function fails, -1 will be returned as SSM ID with the actual error specified in the error number variable. I have been referring to this variable for past 3-4 lectures, that is a system variable which is defined, which you can use with the error directly with the printf in case it returns an error. Create 64 KB memory segment with the error return if the segment already exists with the key ID of hexadecimal 123. So we can give expression, if you notice here 64 into 1024, the ID, IPC create, ipcxl, and the permissions. Finally, we look at a simple example of finding the shared memory identifier of an existing segment. So we specify shmget, we specify the ID. If found, then found the ID. If not, then if you notice, we are passing 0 as we discussed in the previous slide, that we specify the identifier and we specify 0 as the second argument. Then shared memory ID structure, DS, the data structure which was referred in the walkthrough. The shared memory data structure that is contained within the kernel. This is the complete structure. Look at what we have: shared memory data structure, IPC permission, SHM permission, access permissions for this, SHM size in bytes, last attach time, last detach time, last change time. So shared memory AT time, DT time, CT time, that is C time, A time, D time, C time. Then unsigned short CPID, that is the PID of the segment creator, LPID segment of last segment user, and SHM attached number of current attaches for the same segment. these are the fields of this data structure, shmid_ds. And the IPC parameter, which is used here as a structure in the first line, in the second line, this is the structure of that IPC permission. So these are the permission: unsigned integer short user ID, group ID, C user ID, CUID, that is creator and user. You remember that, creator and owner. Then mode. Alright, so these are the permissions for the permission set structure. After creation, SHM permission structure is initialized with the value, with the key and the creator's user ID and the group ID. Shared memory data structure init on creation. So after initialization, you will get these values default. SHM segment SZ, segment size provided to shmget, access time 0, attach time 0, detach time 0, C time current time, CPID current process ID, calling process ID, LPID 0, and attach is 0, CUID creator process user ID and group ID. These are the values when you create for the first time, the default values which are entered. Then comes the shmctl function, shared memory control. The shmctl API function provides three separate functions. Read the current shared memory structure using ipc stat command, write the shared memory structure using ipc set command, and remove using rmid. So the prototype of the function is initial integer value, the ID of that shared memory, command, and structure shmid and the buffer. Removing the shared memory segment. To remove a segment, we must first have the shared memory identifier. We can use this using shmget. We then pass this identifier along with the command ipcrmid to shmctl. So shmid, shmget command used to get that. If not equal to -1, then we are using shmctl, shmid, ipcrmid. This will be removed. If no processes are currently attached, then the segment is removed. If there are currently attaches to the shared memory segment, then the segment is marked for deletion but not yet deleted. This means that only after the last process detaches it from the segment, then this segment will be removed. Once the segment is marked for deletion, no processes may attach to the segment. Any attempt to attach results in error written into the error set to EIDRM. The IPC stat command example in your program, shared memory data structure element accessible through shmctl. So refer to this program. We are creating shmget size of, get the size of memory segment identified by my shmid and then use it. So this is the complete program. The IPC stat command can be used within shmctl to gather information about the shared memory segment. After getting our shared memory identifier, we use shmctl to grab the shared memory structure. On success of shmctl, what we do is we emit the various accessible data elements using printf. At line number 27 and 31, if shm access time, that is A time, is not equal to 0, and 31, line number 31, D time, detached time, not equal to 0, we check that the time values are non-zero. If there have been no attaches or detaches, the value will be 0. As I mentioned in the slide in the form of table, the default values, what will be the values if there are no attaches or detaches, and therefore there is no reasons to convert it into a string time. IPC set command, this permits the caller to update certain elements of the shared memory segment data structure. It's important that the shared memory data structure be read first to get the current set of parameters. What are the writable elements? Same set of parameters, we discussed that earlier also. So similar, I'm not saying same, similar. SHM parameter, user ID, group ID, flags and time. These can be changed. These are writable elements. So how do we change them? With example, changing access permissions in shared memory segment. So here we are changing shared memory line number 27. If you refer to this line number 27, SHM shared memory permission mode equal to unsigned short, and we are setting it to 044. And then CTL, this time also we are also changing this SHM CTL, SHM ID, IPC set, SHM IDs. So these two lines helps us understanding that how can we change, and this is another setting, SHM CTL, IPC stat. So this is new permissions are changed in this example. Shared memory has the ability to lock down segments so that they are not candidates for swapping out of memory. This mechanism is therefore very useful from the performance standpoint. The SHM CTL API function provides the means both to lock down a segment and also to unlock. Lock and unlock a shared memory segment. Shared memory, SHM ID, we get the ID, shared memory lock and lockdown. So point to be noted, SHM lock. Locking the segment is similar, we use SHM unlock. SHM CTL, SHM ID and the unlock. As before, a 0 return indicates success of the SHM CTL command. Only a super user may perform this particular command via SHM CTL. Therefore, when you try this command, when you try this example, you should be logged in as a root user. SHM attach API function. After the shared memory segment is created, a process must attach to it to make it available within the address space, and this is provided by SHM attach API function. And this is a call to the function SHM we pass that address and the flags in addition to the ID of the shared memory segment. This takes shared memory segment identifier as a set of flags. The desired address SHM ADDR is rounded down if the SHM RND flag is set within SHM flags. To have the SHM attach API function automatically place the region within the process's address space, we must use a casting function, the casting of this void type pointer, constant void pointer type, null argument. This must be passed. The caller can also specify SHM read only within the SHM flags to enforce a read only policy. This process must have read permission on the segment. If SHM read only is not specified, it is assumed that segment is being mapped for both read and write. and there is no write-only flag. The return value from SHM attach is the address in which the shared memory segment is mapped into the process. Let's look at the one example of SHM attach. Get the SHM ID of the shared memory segment, map segment into our space, SHM attach, SHM ID 00. If it is successful, attach. If it is -1, it is failed, otherwise it is attached or succeeded. On completion, my address will contain the address in which the segment is attached, or -1 if it is failed. The return address can then be utilized by the process just like any other address. The example of SHM attach. On successful completion of this SHM attach call, the shared memory data structure is updated as the A time field will have the current time, LPID is updated with the effective process ID of the calling process, and an attach field is incremented by 1. That who all are using this. When a process exits, its shared memory segments are automatically detached. Despite this, developers should detach from their segment using shmdt rather than relying on the GNU Linux to do this for them. So the DT API function, this function shmdt detaches an attached shared memory segment from a process. When a process no longer needs access to the memory, this function frees that. And this is a call. We just pass the pointer. The caller provides the address that was provided by SHM attach as its return value. A return value of 0 indicate a successful detach of the segment. This is example demonstration of shmdt call. We get the value, get the IDs existing, map this segment into the space, that is attaching it, detach or unmap it. So get the address and then remove it. shmdt my address. We just pass it and it is detached. On successful detach, the shared memory structure is updated as the D time field will be updated with the current time. LPID is updated with the process ID of the process calling the shmdt, and SHM and attach field is decremented by 1. The address region mapped by the shared memory segment will be unavailable to the process and may result in a segment violation if the access is attempted. If the segment had been previously marked for deletion and the number of current attaches is 0, then the segment is removed. Coordinating access to a shared memory segment. The shared memory can be a powerful mechanism for communication and coordination between processes. With this power comes some kind of complexity. Since it is a resource that's available to all attached processes, we must coordinate access to it. One mechanism is to simply add a semaphore to the shared memory segment. A simple application that provides creating, using, removing a shared memory segment is our next example. Our shared memory block is type def. This contains our shared memory structure, a counter, and our semaphore to coordinate the access. So this is this example, shm example.c in your source code. Shared memory example using semaphore coordination. This is the type def structure I was referring to, my block T. And this is the program segment, the important part. Our scenario begin by grabbing the user's character passed as the second argument from the command line. This is the character we'll place it into the buffer on each pass. We'll invoke this process twice with the different characters to see each access the shared structure in a synchronized way. We then loop through to a count of 2500, each iteration acquiring the semaphore, loading our character into the string array of the shared memory segment, and then releasing the semaphore. This is the rest of the program. The program is quite comprehensive, so you need to spend time on this program. This is a write block, if you see carefully. This is a write block, this is a create block. So it is divided into different blocks. So shmget, attach it to it, we are attaching it, and then we are count of 2500 as was mentioned in the previous slide. So this is the explanation of the entire. The rest of this, like setting the values, is quite easy. We are passing this. This is continuation of the same program. Quite lengthy program if you notice. This is create read block. So create block, write block, read block. We are divided into separate blocks, and reading or writing is not difficult. We are displaying the value, terminate the buffer, printing the counter, and program and share remove block. So when we run this example, we create our shared memory segment and then execute our scenario one after another. We specify two different characters to differentiate which process had control for what position, for that position in the string. Once complete, we use the read command to emit the string. So we are creating it, use A, use B, then we are reading it, and then we are removing it. There are user utilities for this, the IPC utility, which is the same thing. ipc-m, this will present all the shared memory segments that are visible to process. To create, we already have the programs executable created for this, shm create, shm-n, and this is the output, a screen grab of the output. And if you notice, this is what we have created. We see that a new shared memory segment being available, size being 32819 bytes, and we see that there are currently no attaches to this segment. The user utilities for this. If we wanted to dig into the segment deeper, we could specify the -i option, the way we have used it in the earlier examples. So -m-i, the identifier. Finally, we can remove the shared memory segment using ipcrm, and it will remove that. So this is the screen grab of the sample run. So what we learned, the summary. We introduced shared memory in GNU Linux and the API that control its use. We first introduced the shared memory API as a quick review and then provided a more detailed view of the APIs being used. As a shared memory segment, we can As shared memory segment can be shared by multiple synchronous processes, we illustrated the protection of shared memory using a semaphore. Finally, we reviewed the ipcs utility and demonstrated its use as a debugging tool, as well as the ipcrm utility for removing shared memory segment from the command line.